Haloalkanes undergoes two types of reaction. These are elimination reaction and nucleophilic substitution reaction. For the elimination reaction, actually we had learned this in chapter 5, which is 5.2, the preparation of alkenes. If you still remember, the reagent, which is our alkyl halide or haloalkanes, in the conditions of base such as potassium hydroxide in alcohol or alkoxide ion, heat or reflux. The products of this reaction is an alkenes. So in this reaction, we are going to eliminate our halogen and also the hydrogen that attach to the adjacent carbon, which is the neighboring carbon. So if we have a symmetrical carbon like this, okay, CH3, CH3, CH3. So since these three alkyl groups are symmetrical to each other, if we remove the hydrogen from any other carbon here, all right, the hydrogen on this carbon or this carbon or this carbon, it still will give us only one product of alkenes, which is 2-methyl-propene. So the name of this reaction is dehydrohalogenation. Okay, since we are going to eliminate the halogen and also the hydrogen from the adjacent carbon. In this example, alright, so we have a halogen on this carbon. Okay, so we can eliminate the hydrogen on the adjacent carbon from this carbon or this carbon or this carbon. So since these two carbon are symmetrical to each other, so if we remove the hydrogen from this carbon or this carbon, we will still get the same product, which is 2-methyl-1-butene. But if we remove the hydrogen from this carbon, alright, so since this carbon is not symmetrical to these two carbon, alright, so if we remove the hydrogen on this carbon, we will get the second product, which is 2-methyl-2-butene. So since we have two different products of alkenes here, we can determine our major product according to Sazaf's rule. So Sazaf's rule states that in elimination reaction, major product is the most stable alkene, okay, commonly most highly substituted alkene. So let's have a look at this first product. So this is our carbon-carbon double bond. Alright, so since here we have two alkyl group attached to the carbon-carbon double bond, alright, but for the second product, alright, so this is our carbon-carbon double bond, and here we have 1, 2, 3 alkyl group attached to the carbon-carbon double bond. So since the second product is the most highly substituted alkene, so this one is going to be our major product. So in this case, this is our compound B and this is our compound A. The most important reactions for haloalkanes are nucleophilic substitution reactions in which the halogen atom is substituted by a nucleophile. We will have a look at the reaction of haloalkanes with several different types of nucleophile. So the first one here, we got the hydroxide ion. So for the reaction with hydroxide ion, the hydroxide ion comes from the sodium hydroxide aqueous solution, okay, where in the sodium hydroxide, so we have the hydroxide ion and sodium plus ion, okay, or in the potassium hydroxide, so same here we have the hydroxide ion and the potassium ion. So in this case, our nucleophile is the hydroxide ion, alright, where the hydroxide ion will replace the halogen atoms in our haloalkanes and it will become an alcohol. The halogen will become the halide ion as a leaving group. The second nucleophile that we got here is water. Okay, for the reaction with water, okay, so here we have water, alright. So same goes to the first reaction here. The reaction with water also will give us an alcohol. So in this case, alright, so we only take the OH group, okay, the OH group will replace the halogen atom and the hydrogen here will combine with the halogen atom and it will become the halogen halide as our side product. So these two reaction is called as a hydrolysis of haloalkanes. The third nucleophile that we got here is the alkoxide ion. So for the reaction with alkoxide ion, the alkoxide ion can be formed from the sodium alkoxide, which is here we have the alkoxide ion and sodium ion, or from the potassium alkoxide. Okay, so here we have the alkoxide ion and potassium ion. So our nucleophile in this case is the RO minus group. So the RO minus group will replace the halogen, and the halogen will become the halide ion as a leaving group, right? So this reaction will give us an ether. Okay, the third nucleophile here we have the alcohol. Okay, so for the reaction with alcohol, all right, so we will take the RO group, all right, so we just take the RO group, and then the RO group will replace the halogen, and then the halogen will combine together with the hydrogen, and it will become the hydrogen halide, okay, as our side product. So same goes to the previous reaction. So this reaction also will give us an ether. Okay, so these two reaction is called as an alcoholysis of haloalkanes. Okay, next our nucleophile is the ammonia. Okay, for the reaction with ammonia, the excess ammonia, so in this reaction, right, we will just take the NH2 group. Alright, so here we have NH2 group. Okay, the other hydrogen here, alright, will combine to another ammonia molecules, okay, and it will form an ammonium ion, okay, and the halide ion will combine together our ammonium ion, and it will become an ammonium halide. Okay, so this is our side product. Okay, the next nucleophile that we got here is the cyanide ion. So the cyanide ion will comes from the sodium cyanide or potassium cyanide. So in this case, we have the Na plus and also the Cn minus ion. So we just take the Cn minus ion as our nucleophile and then replace it with our halogen. Okay, so the halogen will be replaced by the Cn group, okay, and then the halogen will become the halide ion as a leaving group. And last but not least is the reaction with the acetate ion. So we can get the acetate ion from the sodium acetate or potassium acetate, or maybe from carboxylic acid. Okay, so for the reaction with acetate ion, okay, the acetate ion will replace the halogen, all right, and then it will give us an ester, and the halogen ion will become a halide ion, which is the leaving group. So let's have a look at example on how are we going to predict our product. Okay, so for the first reaction, so we have an haloalkane, so Br is our halogen. Okay, so it will react with the potassium hydroxide aqueous solution. Okay, so since we have the potassium hydroxide, so we know that our nucleophile in this case is only the OH group. So in this case, okay, right, so here just now we have the Br, okay, so just replace the Br, okay, with our OH group, right, so we have the OH group, okay, so this is our product, which is an alcohol. Okay, for the second reaction, all right, so here we have the halogen, the Br group, okay, and here our nucleophile is water. Okay, so since we have water here, right, so remember if we have water, okay, the nucleophile, okay, that we replace the Br here, okay, we will just take the OH group from the water. Okay, so just copy back our structure. So since here we have the Br just now, so just replace it with the OH group, right? So the third one, okay, so we have the Cl here on this carbon. Okay, so since we have the alcohol, okay, we have the alcohol, so remember from alcohol our nucleophile is going to be CH3O only. Okay, so we just take the CH3O. Okay, so let's copy back our structure. So this is our structure, and then on this carbon we have the Cl just now. Okay, so we are going to replace it by OCH3. So remember, okay, on this molecule, okay, on these alcohol molecules, the one that the one that will attach to the carbon here, okay, is the oxygen, okay, not the carbon, not the hydrogen, it is the oxygen. So since here the oxygen originally attached to the hydrogen, so this oxygen is going to be incomplete octet. Okay, so that's why the oxygen will bonded to the carbon here. Alright, so next we have the reaction with KCN. Okay, so this is our Br. Okay, so the reaction with KCN, our nucleophile here is the cyanide ion, the Cn minus. So just copy back our haloalkanes. Okay, so this is our haloalkanes. Right, so since we have originally Br attached to this carbon, so just replace the Br here with the Cn group. Right, next we have the reaction with acetate ion. So here, right, our acetate ion is going to be, right, so if you open the structure, so we have CH3, CH2, C double bond O, O minus. Okay, so the oxygen here we attach to the carbon that originally attached to the halogen group here. Right, so let's copy back our structure. Okay, so since here we have Br originally, so we are going to replace the Br with this oxygen. Okay, so we have O. Okay, and then just copy back our structure, and then next to it we have C double bond O, and then CH2 CH3. Okay, so this is reaction with acetate ion, so we are going to get our ester as our product. Okay, alright, so next we have an alkoxide ion as our nucleophile. Okay, so this is our Cl. Alright, so just copy back our structure. Okay, so since originally here we have the Cl group. Okay, so here the one that we bonded to this carbon is the oxygen. Okay, so O, and then copy back here we have CH, and then CH3 2. Okay, just copy back all of this. Okay, and then last but not least we have Cl here. Okay, and then reaction with the excess ammonia. So remember, for the reaction with excess ammonia, we'll just gonna take the NH2 group. Okay, so just take the NH2 group to replace the halogen. Okay, so here we will get, okay, the Cl will be replaced by the NH2 group. But if we further react our reaction with the haloalkanes, okay, since we still got the hydrogen on the nitrogen here, right, so what we're gonna do is, okay, so we can take out the one of the hydrogen. Okay, so now, right, so the our nucleophile here is going to be CH3, CH2, and H. Okay, so just copy back our structure. Right, so here we have the NH, and then here just take the CH3 group. Okay, then this nitrogen will attach to the CH3 group. So now we will get the secondary amines. Okay, this is a primary amines and this is the secondary amines. And then since we still have the hydrogen on the nitrogen, again we can further our reaction with the haloalkanes to get a tertiary amines. Okay,